false. Okay. And it is very easy to see examples where that is false. In fact, we can, this is for n equals 4. We can just extend even to n equals 2. We can say, can we have, for example, for k equals 2, can we have y1, y2, just zi plus 1 positive? Is that enough? And already the case n equals 4 shows us why this is not enough. So this is like having a positive matrix where you say the minors 1, 2, 2, 3, 3, 4, and 1, 4 are positive, but you don't say anything else. So this is a 2 by 4 matrix. Now there's a Schacht relation that says 1, 3, 2, 4 is 1, 2, 3, 4 plus 2, 3, 1, 4. And when you're in the positive Grassmannian, for example, you also say that 1, 3 is positive. So you see, if 1, 3 is positive, all of these guys are positive, and 2, 4 must also be positive. But in general, if you say nothing about the signs of these guys, could either both be positive or both be negative. Okay, so it is not enough to just specify that these I plus 1 boundaries are positive. Okay. However, there's one more way we could talk about going back to the polygon. One final way we could talk about whether you're in the polygon or not is to say you're in the polygon if you look at the boundary points, 1, 2, 2, 3, 3, 4, right? And if you imagine you going around, if they have winding number 1 around y, okay? They wind once around y. So in the case of the polygon, there seems to be 3 equivalent descriptions. C dot z on the right side of the boundaries and winding number 1. It turns out that being on the right side of the boundaries and having winding number 1 are accidentally the same condition for polytopes. In general, there are different conditions. And what you have to do when you go to the amplituhedron is specify both the inequalities and the topological condition that the z's have the right winding number. So I can illustrate it geometrically quickly, and then I'll end. So imagine in this case, so we have y as a 2-plane. The z's live in 4 dimensions. So the z's are 4-dimensional vectors. But imagine projecting through y. Okay, so projecting through y, literally looking in the direction of the 2 y's to go from 4-dimensional vectors to 2-dimensional vectors. Okay, so in this projected space, which is literally a 2-dimensional space, we have the origin. That's where y went. And then, I can have z1, z2, z3, z4. I can have any shape like this. If I say that all the I plus 1s are positive, it just means that everything has got to wind around always clockwise around the origin. But for example, with 4 points, there's 2 ways that can happen. You can have something like this, or I can have something like this. This has winding number 0. This has winding number 1. And the claim is that you have to have maximal winding number. You have to have winding number 1 in order to be inside the amplituhedron. In general, for general k, for m equals 2 in general k, the condition is always y1 through yk, zi plus 1, zj plus 1. Sorry, zi plus 1 is positive. And in this 2-dimensional space projected through y, the zi plus 1 have to have winding number which is maximal, and the winding number which is equal to 1, 1, 2, 2, 3, 3, so k equals 1, k equals 2, k equals 3, and so on. In general, it's k plus 1, the floor of k plus 1 over 2. So you have to be on the right side of the boundaries and satisfy the topological condition that the z's wind around maximally. That's for m equals 2. For m equals 4, you have to be on the right side of these boundaries. And now you have to have the z's, which are now just the ordinary. Now, let me stress this point. Now the picture that we're talking about, when we project through y, the z's that we're talking about are literally the ordinary bosonic momentum twisters now. There's no more funny k components, they're all gone. You could ask a natural question. If the z's were positive to begin with, in this 4 plus k dimensional sense, what would they look like in this 4-dimensional space? Would they also look positive? The answer is no, in general. They look different. They satisfy a different condition. The condition they satisfy is a topological one, that the set of z's has maximal winding number. Now, in the sense of 3-dimensional winding. Okay. Instead of taking there we took the line segments I plus 1. Here, we take the 3-dimensional segments made up out of all the I plus 1, jj plus 1s. And that 3-dimensional segment winds around the origin a number of times that grows like the square of k, like k choose 2 roughly. Instead of linearly with k, it goes like k. Okay. The y is gone in this picture. There's no more y, there's no more positive Grassmannian, there's c is gone. Okay? C is gone. Everything is now completely described in terms of physical things about the actual bosonic momentum twisters. Okay? Is that, and it's purely being on the right side of all the boundaries, and this topological condition tells you, defines the space, and then that space factorizes properly the singularities in the right spot, and so on and so forth. Okay? So there's more I can say about it, but I've obviously run out of time. What this shows is that whatever this dual object is, it has to know more than just about a bunch of boundaries. Okay? It has to say something about these topological conditions as well. But it's an encouraging sign that we're getting rid of the C's. Okay? We're getting rid of all this, because even the C's were rather redundant extra stuff, right? Now we can describe what the amplitudhedron is as the effect that it has purely on the bosonic data. Well, there are some further developments along these lines, but I will leave it at that. Thank you.
Time for a couple questions.
If you conjecture the right-hand side to be straight, why don't you just triangulate it?
Sorry?
Triangulate it, the worksheet, and see if you get.
Oh no, I mean the problem is that this is going to be it's not really, it'll hopefully turn into a smooth string worldsheet of strong coupling. But the whole point is that it's supposed to turn into something else at weak coupling. And the something else at weak coupling is the spin chain. Well, there's probably something that doesn't care about the coupling at all. And it's some discretized version of the worldsheet, whatever this funny integrable spin chain is, which is underlying all of this magic from the integrability side. But it's not very usefully thought of as a worldsheet at the weak coupling. But what I really meant is that there are many steps in this thought, any one of which could fail. Okay, but there's no way we're going to go from this integrand that looks like it comes from gluons to anything that looks like a flux loop. No way in hell. Okay, so the only way it could possibly work is to get something which is talking directly about integrated expressions. Okay? But if these two worlds are not going to talk to each other at all, then so be it. On the other hand, there's a reason internal to the world of the integrand why you should want such a representation, right? I've given you a number of them. And if you had one of them, it sure looks like it would make it easy to integrate and replace the integrals by replace the loop integral by integral over these dual variables. So it seems since that's needed for the internal logic purely starting from the integrand side, or it'd be a nice thing to happen purely from the internal logic of the integrand side, and it has something that it could match onto it on the other end, then it seems a pity if it was false. By the way, I mean, just to say that this fantasy is much closer to seeming like it might be true than many of the other fantasies that I had about this business 5 or 6 or 7 years ago. So it seems it seems much. I mean, that there's more. Yeah, I think it's this is not going to be either. It's completely wrong. It's not going to take 10 years to figure out. Yeah. I think it's either completely wrong or it's pretty close. Yeah.
So since then we're coming back to the external data.
Yes.
Is there any advantage in thinking of in terms of back to those cell structures that you have different dimensional cells where you get the positive region of the external data?
For the external data, yes,
Yeah.
there may very well be. There may very well be. Yeah, certainly we haven't thought about it so much about what the amplitudes look like when you go to lower dimensional cells in the external Z space. One reason you might be wary is that well, in the Z space, in the 4 plus k dimensional Z space, there certainly should be. But I think much more interesting is that there's going to be some extension of positivity just in the 4-dimensional bosonic momentum boosters. Because there, but it's not just positivity, it's extra positivity. That's these, this business of it winding tells you that it's not just positive. Just the 4-dimensional data isn't just positive, it's more than positive. It satisfies more constraints. Okay? And so I think there's very likely some analog of a cell structure on that space, and that is going to I hope it's going to be useful. For example, Mark et al. See all these remarkable cluster variables, right? And there's no understanding for why we get those funny cluster variables showing up. It's purely in the space of the external bosonic momentum twisters. Just in the positive Rachmanian, if all you know is the positive Rachmanian for the external data, there's no reason to talk about those. But if you imagine that there's an extended cluster structure on the external 4-dimensional data, then it might force you to use some of these other variables as well. So that's where I think more interesting stuff is to happen. I think if you just take the external Z's, 4 plus k dimensional Z's, and go to boundaries, probably something will happen, but I doubt too much.
Do you think these smart versions of fine parameters are analogous or even equal to the parameters you integrate over to the iterated integral, for instance?
Exactly that.
Yeah.
It's 100% that. In fact, I didn't have time to give. I mean, we have one example, one very simple example for the n equals 2 amplitudhedron where we can understand everything, including this dual formula and all of that stuff makes sense. And the simplest version of that is just MHV one loop. Okay. But in that case, it gives you a representation. The only representation I know, and you start with the integrand and you turn it into dialogues, and it's obvious why it's dialogues. You don't nowhere in the process does a little miracle happen, some total derivative happen. It goes from integrand to dialogues, and not but a representation for the final answer in this sort of most invariant way of writing the dialogues in this Aomoto form. So what I mean is that let me say a more precise version of the fantasy is that when you take the final polylogarithmic object, say, and you write it as a sum of a bunch of iterated integrals, what you're doing is sort of chopping it up into pieces and forcing each piece into the same simplex over and over again, the same iterated structure over and over again. It's plausible that instead it wants to be represented as an integral over some region, right? So just like, let me just give you the sort of dumbest version of this. Like if someone tells you what is a dialogue is dialogues are the integral dx over x dy over y over some random triangle in xy space, right? Those are what dialogues are. But so if someone actually tells you do the integral dx over x dy over y over that funny shaped region, right? Of course you could take this region, break it up into triangles, take each triangle, put it in standard form, and write the result as a sum of a bunch of dialogues. You could do that. But it's sort of smashing the object up into pieces. It would be much better. You'd be much better served being told that it's the integral over that pentagon. That's what especially in local forms, we finely parameterize them. It's the analog of taking something which is, more naturally given as an integral over some nice region, breaking it up, and then taking each one and bringing it some canonical form. And so it's, and of course, you guys know and experience it in life much more than us outsiders do. All these incredible, humongous cancellations of the symbol, all this incredible magic when you put these things together, look like there's some large, there's a collection of objects that are being broken apart and are to be put in some canonical form, and then something nice happens when you put them back together. Already just as toy examples. And by the way, the sort of nicest way of representing a dialogue, the nicest way of representing a dialogue is projectively like this. So it looks a little bit more abstract. But if you say that W lives inside some triangle and Y lives inside some dual triangle, they don't have to be duals of each other. Just some triangle 1 and some dual triangle 2. Then you have this beautiful canonical form on the product of two projective spaces. And this form makes, and so this is called the Aomoto dialogue. If you put this in general two simplices, a simplex there and a simplex there, they're the Aomoto polylogs. This is a form, let's say, for the dialogue, that all the dialogue identities are the statement that if you make this a square and you triangulate this way versus triangulate that way, you get the same answer. Okay? So all of the identities of the polylogs are made manifest in this definition of what in this definition of the polylogs. But other things are made manifest. For example, here it doesn't look like, here it looks like a four-dimensional integral, right? It doesn't look like a two-dimensional integral. It looks like a four-dimensional integral. But this is the total derivative in W and in Y separately. So if you use Stokes' theorem, you take it down to a two-dimensional integral with a boundary, which gives you the usual way of thinking about dialogues, or four-dimensional integrals without boundary, which is another, which is the more invariant representation of dialogue. Now, so this is just a nice definition of dialogue. But if I gave you a function which was secretly, W inside some polygon and Y inside some other polygon, and I didn't tell you what the polygons were, then you could spend a long time staring at the symbol back and forth until you figure out that what's going on is just these two simple guys. Right? That's what I think is going on with the loop integrals, or and whether we get them from fine. Now, when we get them from fine parameterization, it's even more inefficient because it doesn't immediately come out with the right transcendentality and so on. But I think ultimately, but one way or another, once you get into the right transcendentality, there's sort of pieces which are not, which know too coarse amount of information about the theory. They know about the denominators and not the numerators. And we know there's a lot of magic in the structure. Anyway, so long answer to your more succinct and good question. But yes, I suspect that these